Well, a couple of words more. This allows us, starting with a new concept, which is the velocity. Sorry, exactly the velocity. The velocity is the time derivative of the equation of motion. Sometimes you get confused with that. We said, well, this is the material derivative of the equation of motion. No, no. The concept of material and spatial derivative doesn't apply to equations of motion. Equation of motion is just a function of the material coordinates and time, so the only concept is derivative with respect to time. There is no exact sense of talking about material derivative of equations of motion. Every time derivative of the equation of motions is a material derivative, because intrinsically equations of motions are given in material description. So anyway, if I had the equations of motion, the derivative, the partial derivative with respect to time, returns the velocity. And naturally, this velocity would be given in material description. That's what we had here. When I got the velocity here, since I differentiate the equations of motion with respect to time, I have some expressions that are given in material description in terms of the capital coordinates. Okay? Of course, I could have obtained the spatial description of that by replacing the inverse equation of motions in there. Okay? So then, once I have the material description of the velocity, if I replace the inverse equation of motion, so the capital X as a function of the small x and time, then I will obtain as function of function a function of a small x and t, which is the spatial description. Okay? So I could always do that. Whenever I have a material description of a property, I could think that I would, if necessary, be able to obtain the corresponding spatial description just by replacing the inverse equations of motion. Or the opposite, if I had the spatial description, I could obtain, if necessary, the material description by inserting the equations of motion. So that's always possible. So that's the definition of velocity. You know that always this is the compact equation, the compact definition, and this is the component. There are three components, each one being the derivative of this with respect to time. Acceleration. What is acceleration? The definition of the acceleration is the derivative of respect to time of the material description of velocity. So the right definition of acceleration is the material derivative of a property, of a velocity, sorry. Accelerations, the acceleration of a particle is the material derivative of the velocity of this particle. Okay? So now this velocity can be described either in material form or in spatial form. If the velocity is described in material form, just I differentiate with respect to time, I take the partial derivative of the material form of the velocity, and I obtain the material description of the acceleration. But if I wanted to obtain the spatial description of the acceleration, what I could do is just, in that expression of the acceleration, by the way, denoted by capital A. Capital A corresponds to the material description, so we use a capital letter, and then if I replace in here the expression of the equations of motion, I would obtain something which is a function of a small x and t, which is the spatial description of the acceleration. But look, if I only had a spatial description of the velocity, I could obtain that spatial description of acceleration. How? By using the concept that material derivative of a spatial description is the local derivative plus the convective derivative, which is b times the spatial gradient of b. Okay? So just something that shows the power of this concept of a material description of a material derivative of a spatial description. Okay?
Consider now a motion, a rigid body motion of this body, which turns at a constant angular velocity, w, it just turns around the origin of coordinates in that way. So at t equals 0, the body is placed in that position, that would be the reference configuration, and as time goes on, then the original angle of every position of the particle phi just increases in an additional angle which is the angular velocity times time. So at times t, that particle moves to that particle, and the radius being the same, the distance being the same, the angle, the position angle with respect to axis y is phi plus omega t. Okay? So what are the equations of motion for that case? Well, it's very easy. So the coordinates of this particle at times t would be that projection and that projection. The x coordinate would be that distance, the y coordinate would be that distance. How can we compute? Okay, x component would be r sinus of this angle, sinus of omega t plus phi, and the y component would be r cosinus of this angle, r cosinus of omega t plus phi. So that provides for every time t the spatial coordinates of a given particle. Look, this is a specific case in which these, which could be considered the equations of motion, are not given in canonical form. Why? Because when I replace t equals 0 here, I should obtain here capital X, and here capital Y, and I don't obtain that. So, in other words, that is the feasible alternative, that every motion can be described in non-canonical form. Every particle is now described in terms of what? Well, some values r, which is the original distance of the particle in the reference configuration to the origin, and phi. Phi is the original angle at this time. So r and phi are, so to speak, the label of the particles. R and phi, R and capital Phi, identify the particle, univocally the particle at the reference configuration. Okay? But these are not the coordinates of the particle at the reference configuration. They are not this x coordinate and this capital Y coordinate. So this is a non-canonical description of the equation of motion. Should we compute the canonical equations, which could be considered in that time, for doing that, we have to just replace for t equals 0, we see that for t equals 0, we obtain that the right-hand side of this equation is r sinus of phi. And the right-hand side of this equation is r cosinus of phi. For t equals 0, this term drops. So this should be capital X and capital Y, the material coordinates of the particle. So, okay, that is what it identifies X and Y, capital X and capital Y. So in order to obtain here the canonical description of the motion, we have to solve R and phi here in terms of X and Y, capital X and capital Y, and replace here. And that's what we are doing here. So after some algebraic operations, I'm not going into details because it's something that you can look at in your homework. But then we solve here R and phi in terms of X and Y, and we obtain the description of a small x, a small y, the spatial coordinates, now in terms of capital X and capital Y, which is this here. This is the same thing here. But instead of describing or identifying the particle by the label, the two parameters, capital R and phi, which are capital R is the distance, capital phi is the distance, now we identify the particles by the Cartesian coordinates at the reference configuration. And that's it. And that's it. So now, this is the canonical form of the equations of motion for that. Look that if we place t here, t equals 0 here, the reference time, what we obtain here? X because this is 1, this is 0, so we obtain small x equal capital X, and here this term drops, and we obtain a small y is capital Y. These are the canonical equations of motion. Okay? So this is the same, but just with some algebraic operations in order to get the canonical description of the motion. Okay. So now maybe we are interested in obtaining the inverse equation of motions. What should I do to obtain the canonical equations of motions? Well, isolating these equations, capital X and capital Y, in terms of a small x, small y. So that is done here, okay? By just isolating, capital X is that, after that capital Y is something else. So finally, the inverse equations of motions are that. So, at the beginning of the problem, so to speak, in this body which is moving in a uniform angular velocity rotation around the origin of coordinates in a velocity y, the equations of motions that identify the position of every particle at time t in terms of the position of these particles at time 0 are these, and the inverse equation of motions that identify what was the particle capital X, capital Y, that at the present time occupies the position small x, small y, are those. Okay? These are the inverse equation of motion, capital small x as a function of material coordinates and time, and the inverse equations of equation that provides the material coordinates in terms of the spatial coordinates and time. Okay? So now we are ready to start. Okay, so now we have the equations of motion. Let's compute the velocity. What do you have to do to obtain the velocity? Well, differentiate this equation of motion with respect to time. So if we differentiate this with respect to time, the first one, we obtain that equation. And that is precisely the component x of the velocity. And by differentiating that with respect to time, which is down here, we obtain the component y of the velocity. Look that expressions are given in terms of capital X, capital Y, the material coordinates. So this is an expression that provides the velocity in terms of the material coordinates and time, because velocity is changing. Okay? The velocity of the particles, as they move circularly, following a circle, then the velocity change, and that is the expression that gives that. And that is the material description of the velocity. Okay? If we would like to obtain the spatial description of the velocity, what should we do? Replace in here the inverse equation of motion. So let's do that. That was where the inverse equation of motions, that were the direct equation of motion. This was the expression of the velocity. So let's replace these equations, capital X as a function of small x and y, and capital Y as a function of minus 1, let's them replace in that. So by doing that, and after taking into account some algebraic and some trigonometric expressions, after some operations we obtain that equation here. The first component of the velocity is omega, the angular velocity, times the spatial coordinate y. And the second component of the velocity is minus omega times x. Okay? So that means that now, for this motion, for this particle, at every point xy, I can identify what is the velocity of every particle, of that particle that at the time t occupies the position, small x, small y. And that, you can see that this is a vector that has this direction. It's a vector which is orthogonal to that other vector, because it's a motion, okay, in which the particles follow circles, paths which are circles with center 0, and that particle follows this circle. Okay, so that's what is expressing that. Look, there is something interesting here. Look, the expression of the velocity doesn't depend on time. The spatial expression of the velocity doesn't depend on time. What does it mean? That at a given x and y, the velocity is always the same. Does that mean that the particles have constant velocity? What would you say? So in that motion, do the particles have a constant velocity? As apparently it's said by here, constant along time, I mean. The velocity doesn't change along time. Do the particles have a constant velocity? So is that saying that the velocity of the particles are constant along time? No, because the velocity of the particles is given by that expression. That expression here, which does depend on time. Okay? So this says that a certain particle has a velocity which does depend on time. Time is here. But what is saying that then? That is saying that in a given point of the space, the velocity that at a certain time occupies that position have always all the particles that a long time occupies that position here in that given point of the space, they always have the same velocity, which doesn't depend on time. In fact, all particles occupying that position a long time, they have the same velocity, which is a velocity tangent or orthogonal to the radius vector. So be very precise about what every expression means. That's something that we will look at, or we will look for in the exams. We would like to see if you have these concepts rightly interiorized. Okay? Okay. So this is the spatial description of the velocity, which doesn't depend on time. And this is the material description of the velocity, which does depend on time. So, now let's think about accelerations. What are accelerations? Well, the definition of the acceleration is what? The material derivative of velocities. So, if we look at the material description of the velocities, which is that, and we differentiate with respect to time, we obtain one expression, two equations in fact, one vector with two components, which are these two. So these equations here, with that differentiation, this is the differentiation of that with respect to time, which is this, and this, the differentiation of time, that with respect to time, is that expression here. Okay, or that expression here, sorry. So these are precisely two components, which are the two components of the acceleration. So the acceleration is that. That is the material description of the acceleration. Why material? Because it's given in terms of the material coordinates. It expresses what is the acceleration of a particle at time t, the acceleration at time t, of one particle. What particle? That at the reference configuration occupied the positions capital X, capital Y. Okay? Okay, that's the material description of the acceleration. What about the spatial description of the acceleration? Well, at this time, we have one procedure to get this. Just by replacing here the inverse equation of motion, we'll obtain the same description of the acceleration, but now in terms of small x, small y, which are the spatial description of the acceleration. So let's do that. This is the inverse. These are the inverse equations of motion that will replace in the material description of the acceleration. We replace these equations, and after same operations, we obtain this expression. Look, acceleration again depends first on small x and small y, the spatial description of acceleration. So it's the spatial description of the acceleration. But second, again, it doesn't depend on time. Okay? Which would happen. What does it mean? Does that mean that the acceleration of the particles is zero? Or does that mean that the acceleration of all particles that pass through a certain spatial point, xy, considered fixed, is always the same? And look, this is a vector And if you look at this as a vector, this is proportional to the radius vector. Multiply x and multiply y, so it's a vector that goes, it's a vector that the acceleration that has this direction, this direction. Is that what? Do you remember what is the acceleration of this? This is the centripetal acceleration. The acceleration of a body moving in a uniform constant angular velocity is only what is called the centripetal acceleration, which is a vector which is has the sense opposite to the radius vector. Okay? So that is what it's saying. But you see that this is the velocity in spatial description, that is the velocity, the acceleration, this one. This is the acceleration in material description, this is the acceleration in a spatial description. This game, passing from spatial description, can be done. But now we have another issue here. What if I had only that expression here? So the spatial description of acceleration. And I would like to compute, the spatial description of velocities. And I would like to compute the material derivative of that, so the acceleration. Could I do that? Imagine that I don't have the inverse equations, the inverse motion equations. Could I do that? Yes, because the acceleration is, by definition, the material derivative of the velocity. But if that velocity is expressed in a spatial form, then to compute that derivative, I can compute the local derivative, so the partial derivative of the velocity, the spatial description of the velocity with respect to time, plus b grad b, b times gradient of v. This is what we call the convective derivative of the velocity. So the convective acceleration. Okay? Look, let's do that now. What is the time derivative of this expression? What is the time derivative of this expression? Can you tell me? Does it depend on time? You see time dependence here? You see? So what is the derivative of something that doesn't depend on time? 0. So now the derivative, that derivative here, the local derivative is 0. Okay? And now we have to compute the convective derivative, which is b times grad b. Grad b is a matrix. B is a vector. To do the dot product of a vector times a matrix, we just transpose the first and multiply as a matrix by the second. Okay? So what is the transpose of b? That vector. First component omega y, second component minus omega x. Then what is that grad b? Is a component, is an operation that can be done derivative of respect to x of the vector in the first row, derivative with respect to y of the vector in the second row. That's what you have here. So finally, grad b is that vector. Grad b is the vector whose components are 0 minus b, b is 0. B, transpose of b, is that matrix. Now, we multiply this matrix times this matrix, that is first column, first row, first common, first row, first common, and we obtain two components. In fact, we obtain this vector transposed, but the two components of this, which is this one, are the convective derivative. So finally, what is the acceleration? The local derivative, which is 0, plus the convective derivative, which is 0, so that. And that is precisely the same that we obtained before, as it should be. The point is that I have computed the acceleration from the spatial derivative of velocity with no further information. Just by differentiating that, and I know velocity, I know that. If I know velocity, I know that. If I know velocity, I know that. I can do these operations and finally obtain the acceleration. You see the concept of local and material derivatives, and the result is the same. Velocity is always the same, so the results have to be the same. Sorry, acceleration is always the same. So the result has to be always the same.